Right, right. So in this chapter, we will talk about, actually, it's a combination of three short chapters, which we are going to talk about the wave generation and measurement and interfacing high power components, which is a combination of chapter 15, 14, and 16 accordingly. We'll start with the waveform characteristics. We'll talk about how waveforms are formed, what are the parameters over there, and then how we can generate a waveform in AVR. The input capture, which are all related with the timers again, which we have seen in the previous chapters. And then we will talk about how we can interface high current or voltage components, the drivers, the relays, solid state relays, and the opto isolators. And then we will see two types of motors, stepper motors and their DC motors, how they are operating and how we can control them via AVR. And in the last part, we will see the PWM mods again is related with the timers in AVR. So it's quite important chapter because it's working in a way that they are all in at some point works in an harmony. So they are related to each other. That's why we are covering all these three chapters in one. Okay, so if we start with the waveform characteristics, now the first thing that we need to review, you all know this, but let's just review it. When we talk about period, now what is period? When we have a train of pulses for the clock, for example, okay, the period is from one rising edge to the other one. That defines our period. And the frequency is 1 over period. This is one thing that we need to remember, we need to know. Now, another important one is duty cycle, which we are generally using in a waveform generation. So what is duty cycle? Again, high to low pulses. So we have got, let's say, let's put it this way. That's one period, right? When we think about it. Now, on that one period, either you do it in, like we have done it in the top, like this, or like that. It doesn't matter. First rising edge or the starting from here, it doesn't matter. This is actually specifying the period as well. Now, when we think about the period, there's a high time and the low time of the period. Okay, so this is T0, let's say, and this is T1. Okay, so we have got actually the high pulse and the low pulse. Now, in order to calculate the duty cycle, we just need to do T1, the high pulse, over the period times 100. So this is actually defining the periods where how much is going to be the pulse is going to be 1, and then you can actually accordingly set the low pass. So for example, 50% duty cycle means this is going to be 50 and this is going to be 50. Or if we are talking 80% duty cycle, then 80% duty cycle is something like this. Because this is 80, this is going to be 20 in one period of time. Okay, so this is how we are setting the duty cycle. And we can say that this is equivalent to T1, T0 over T1 times 100 when you think about it. Okay, so this is how we do the duty cycle of a wave. And the last property that we need to consider is the amplitude of the wave. Now, amplitude is high to low, again, train of pulses. The amplitude is where we have got the low level and the high level, and that defines the amplitude of it. Okay, so that's actually the voltage level that we are having. Okay, so if you know the basic things, the parameters about the waves, then we can easily use these terminologies in our analysis and the designs of waveform generation. Now, when we start talking about wave generation, in chapter 9, for each timer, we have seen that there is at least one OCRN register, if you do remember. So OCRN register is the one, like we have got OCR 0 for timer 0, or OCR 2 for timer 2, and OCR 1 A for timer 1, and OCR 3 B for timer 3, for example. Now, the value of this register is constantly compared with the TCNT register. So when we have got the data bus, okay, and we are actually getting a value from here, so OCRN, and we have got TCNT register here, which is a timer register. And these are actually compared in a comparator. Now, when they're compared, what will happen is when they're matching, it is actually going to generate a OCFN flag. Okay, so OCFN flag will be set high. And over here, when they're matching, we can have a tool over here, which we call it waveform generator, which actually going to generate a waveform on OCN pin. Okay, now in each AVR timer, timer 0, 2, 1, 3, there's a waveform generator, and the waveform generator can generate waves on the OCN pin, as I already mentioned. So when we look at the Atmega 128, you can see that there are many waveform generators here. So 7 waveform output pins, OC, which we are going to generate the waves on it, OC 0, 1A, 3A, 1B, 3B, 1C, 3C, and OC2. So in total, we have got 7 waveform output pins and 8 waveform outputs. But OC2 and OC1C, they are sharing the same pin. Okay, so you can see the pins over here as well. So OC2 and OC1C, they are sharing the same pin. You have to configure it through the multiplexer. Okay, so what we are reaching, or what we are checking over here, when the TCNT register reaches to the top or bottom, like we have done it before, or compare match occurs, the waveform generator is informed, okay, which we are going to see the principle over here. So then the waveform generator changes the state of the OCN pin, and according to the mode of the timer, like VGM 01 and 00 bits of the TCCR register, and the COM01 and COM00 bits, they are going to be set, and we are going to generate a waveform. So this is the architecture of it, which you can find in the AVR datasheet as well. So it constantly compares, and match set occurs of OCFRN in the next clock cycle, and different waveforms can be generated based on the VGM and the compare output mode, which we are going to see in a minute. And output compare can be overridden through the force output compare bit to update the OCN pin, and CPU write to TCNT blocks compare matching for 1 clock cycle. Okay, then one thing that we need to be careful, we have to set the OCN pin to be an output pin. And OC0, for example, is an alternative function to PB4 in the Atmega 128, as you can see. So it's PB4 normally. So you can set it as a OC0 and as an output pin. and PB4 as a normal I/O port. So when COM01 and COM00 are 0, it's just a normal output port. Otherwise, pin acts as a waveform generator pin controlled by the waveform generator. Okay, so you can see how these are designed inside of the Atmega 128. Okay, so timer 0 and timer 2 waveform generation is configured through the TCCR register, TCCR0 and TCCR2, and we have got VGMs, which selects the timer mode, normal mode, CTC mode, which we generally use CTC mode, and in the waveform generation, because as I already mentioned over here, that TCNT matches that OCRN with comparing that's two values and set the OCFN and create a waveform. Now, this is going to be in CTC mode. PWM modes, which we are going to see at the end of this chapter, so I'm leaving that for later for now. And in the compare match output, either we can toggle, okay, whenever they are matching, we can toggle, or we can just set it to 0 or set it to 1. So it depends on us how you want to configure it. So non-PWM waveform generation modes in CTC mode, as you can see. Now, you can see the first graph shows the pulse generated by the system clock. And the second graph shows the pulse coming out from the prescaler by 8. So this is a clock divided by 8. So 8 clocks give us a 1 pulse. And scalars can be configured from as if you do remember in the timer lecture, from CSN2, CSN1, and CSN0. So depending on what type of prescaling you want, you can configure those CS pins. And third graph over here, which is TCNTN, which shows actually the count. Now it updates on the falling edge of the pulse coming out of the prescaler. And so what we can see here, the first graph over here, we can see that top -1, which is 254 prescaler pulse. And then on the second one is 255. And on the third one of the prescaler, the TCNT register overflows back to the bottom and to the 0, and then starts again from 1, and it carries on like that, incremented. Now, the fourth graph over here, it shows the OCRN register, and it's only going to be updated when OCFN condition happens. So whenever they are matching, if this is set to a specific value, we have to wait for that. If not, it's going to be the top. So whenever it reaches the top, then OCFN flag will be generated, and we are actually going to inform the waveform generator, okay, generate a wave. So in order to do that, there are a couple of modes, and there's simple calculations related to those that we need to do. And one thing is the FOC 0 that we need to calculate based on the frequency of the clock divided by the prescaling factor. N is the prescaling factor, and OCR 0 plus 1. Okay, so this is prescaling. This is output compare value, and this is the MCU clock. So this is actually the frequency of generated waveform at pin OC 0. Okay, so we can actually calculate that frequency of the waveform generated. So in order to generate these using a timer 0, here is the formula. To generate these square waves, we can set the timer to normal mode or maybe a CTC mode and set the COM bits to the toggle mode. So you can have it as a COM bits as toggling. If I go back, which is 0, 1 for toggle. And the OC pin will be toggled on each compare match and square will be generated. That's the easiest one that you can have. So if we look at the TCNT over here, so we set the OCR0 to some particular value and the TCNT starts to count from 0 to OCR0. Whenever it is matching, compare match is done, so OCFN flag will be high, and then if starts from 1, then it returns to 0, okay, and then stays 0 until the next match, and then it becomes 1 again and stays 1 until the next match, and it goes to 0 again. So this is the formula that we have derived, we can get for timer 0 waveform generation. And if you want to do this for a variable frequencies and the duty cycles, like because this is generated for 50% duty cycles, so we have got 50% high, 50% low, but the frequency is changeable. But you can also have a configurable duty cycle as well. We just need to reconfigure the duty cycle operations and the formula. So at this point, the formula is rewritten as we have got OCR0 first value and the second value plus 2. So you can have different values and you can have a different duty cycles. So the frequencies change, duty cycles also change because you can set different values for the OCR. And the duty cycle can be calculated as OCR1 plus 1 divided by OCR1 plus OCR01, OCR02 plus 2. And this will give us the duty cycle of that wave. So before we move on, one of the important thing in this type of configurations, when you want to generate a wave, important thing is how to set these register values. So register is given over here. Let's say we want to, I'll write the question over here so that we can go through together. So find the TCCR 0 register value to A, set high the OC0 pin upon match, use external clock, falling edge, and normal mode. And B, toggle the OC0 pin upon match, use external clock, falling edge, and CTC mode. Okay, so TCCR register, I'll start with A. Now, force output compare, it can be 0. We don't need to set anything. VGM modes, so it's going to be a normal mode. So we can have 0, 0. So this is going to be 0. And COM bits, we are looking for set high the OCN, OC0 pin upon match. Set high means 1, 1. So COM bits are set to 1, 1. And then VGM N1 is going to be 0 as well, as it is going to be in the normal mode. Then we have got the prescalers. So external clock, there's no prescaling over there, so it's going to be 0, 0, 0. So 0, 0, 0. And that means TCCR CR0, it's going to be equal to, when you convert it to hex, 0 hex 30. Okay? And the second part, part B, it's going to be again force output compare 0. VGM modes, it's going to be CTC, so 0 is the first one. The COM bits, it has to toggle, so 0 and 1. And the VGMN1, it's going to be 1 because this one is 1 over here. And then external clock falling edge, so it's going to be again no pre-scaling. So we are going to get TCCR0 as 0 hex 1 8. Okay, so this is how we can set these registers according to the specifications given to us. Right, so far we have seen how we can do this, and let's do a couple of examples by using these formulas that we have got for generation of a waveform. So the first one is example 1, square wave with 50% duty cycle. So assuming we have got an 8 megahertz clock, generate a square wave with 50% duty cycle and frequency as 500 kilohertz. Okay, now first thing to do is we have to do the calculations. As it is going to be a 50% duty cycle, I can use this formula here. So FOC 0, it's going to be F clock. I'll just rewrite the formula first, and then we're going to put down all the values required. OCR 0 plus 1. Okay, so what is given to us? Now, we know in the question that we will have to generate a 500 kilohertz clock. So this is going to be 500 kilohertz. That's what we want to generate. And we know that we have got 8 megahertz divided by 2. And the scaling factor, we don't know that yet. 2n, and do we know the OCR? We don't know the OCR 0 plus 1. Now that means we have to rearrange this formula so that we can find n OCR plus 1. So n OCR 0 plus 1 is going to be equal to 8 megahertz divided by 2 times 500 kilohertz is 1 megahertz. Okay, so n OCR 0 plus 1, it's going to be 8. Let's say, if we get rid of the megahertz from there. Now, how are we going to do that? Now, it's pretty simple actually, in order to guess what will be the results, because we can say that if we can have the pre-scaling 1 and 8 in this condition, because output is going to be 8. So we can say if n is equals 1, then 1 times something plus 1 will give us 8. So OCR 0 plus 1 should equals to 8. In this case, 1 times 7 plus 1 is actually going to give us 8. Okay, so when n is equals 1, then OCR 0, it's going to be 7. And if we repeat the same thing for n can be equals to 8, then this one, OCR 0, it's going to be 0 plus 1 to get 8. So OCR 0, either it's going to be 7 or 0, depending on the pre-scaling factor. So we can have two alternative ways of writing a code for this. When we think about it, either we can say LDI R20 7 as an OCR value, out OCR 0 R20, and LDI R20. So we had to set the prescalers. So prescaler 1, okay, so no prescaling is 0, 0, right? So, sorry, yeah, this has to be 1, 0, 0, 1. They're not going to be same. This has to be 1. So in this case, it's going to be, so let's write down the TCCR first so that we can get calculate the hex value. So it's 0 VGM mode. It's in the normal mode or in CTC mode. Doesn't matter. So let's set it to 0. And then combits, it can be toggle. Is it normal or toggle? It didn't say anything, so we can use it whatever we want. Okay, and let's say it's going to be 1. And then VGM, that's going to be 1 as well. And then toggle, so this is going to be 0, 0, 1. Okay, so this is going to be 0, 0, 1, no prescaling. In this case, that's going to be 0 hex 1, 9. And then this is going to be out TCCR 0 R20 because we are having a prescaling one. Or we can have the alternative version, which we have already calculated. So this is 1 and 7, and this is going to be 8 and 0. Now, in this case, we can have LDI R20 0. So out OCR 0 will be R20, and LDI R20. So prescaler 8 is 0, 1, 1. So this end is going to change to 0, 1, 1. So TCCR 0 is going to be 0, 0, 1, 1, 0, 1, 1. Okay, so this time it's going to be 0 hex 1. Now that should be 1, 0, not 1, 1. I'm having a problem over here that I have got the double things. I will re-update that. So that's going to be 1A. Okay, so it's going to be 1, 0. Then that's done. And we can say out TCCR 0, it's going to be R20. That's it. So we have got the sets and we have set the numbers for TCCR and OCR 0 accordingly. And that's what we get. Okay, so we can have a few more examples related to these. Which I will do that in the live sessions. So I'll just carry on with the topic. So we can actually give you, I can actually give you the code, and you have to define how this code is going to generate, and you can do the calculations in related to that. And we can also do this in the CTC mode because this we assume that's in normal mode. So in CTC mode, it's better than the normal mode for generating square waves because the frequency of the wave can be easily adjusted using the OCR0 register. So we can actually easily change that in CTC mode. Now, I just want to define that. I just want to show you how we can do it. So for example, let's say I have got two waveforms. This is TCNT0, 0 hex FF, and we have got OCR 0. Right, so what we can have is, based on this, and the similar thing for the OC0, where we have got 1 and 0. So starting with these coming down, maybe I can just point those out. So generating these waves. Now all we need to do is, so starting with 0, let's say, oops, going high at this point, then another much goes down, another much goes up, down, up, down, and so on. So this is how we generate it. Now, in CTC mode, when OCR has a lower value, compare much occurs earlier, as you can see, and the period of the generated wave is smaller, so we can have a higher frequency. Now, when OCR has a higher value, then the compare much occurs later. So if I can generate another one, again, TC and T0, XFF, this is the highest point for 8-bit timer. And if my OCR is somewhere here, then we have to count up more, and then down, and so on and so forth. And when we want to generate this wave, that's going to be OC0, which is 1. And this is going to be generated. As you can see, it's wider as a pulse width. So that means it's going to be slower. Oops. So this is wider. That means we have a larger period and it will be slower. Okay. So when the OCR has a higher value compare much occurs later, and the period of the wait is longer, so we have got a lower frequency. So this is a high frequency. This is low frequency when OCR is higher. So it's like a inverse proportional. Now, please also note that when the compare much occurs, the timer value will be set to 0, okay? And it will restart. Okay, so We'll also do a couple of examples related to these in the live session. And one another thing, so for example, if you want to generate a waveform with different duty cycles, you just need to set another OCR value for the second value. So like we have set over here, you can have a different OCR value, which is going to change in the second cycle, and you can have a wider output, and you can have a different duty cycle at that point. So you can think this as a 40 to 60%. So it's going to be duty cycle 40. That's also possible. So in order to generate pulses using CTC mode, we can configure a timer in CTC mode, and the COM is in the toggle mode. The value of the OCR represents how many clocks it counts before it toggles the pin. And by using this method, we can generate different pulses by loading different values into OCRN register. And in order to load the value to the OCRN, we can use the compare match interrupts as well. So when a compare match occurs, the pin will be toggled and interrupt will be invoked. So by using an interrupt, we can actually define the duration that OCN will be in the current state, and we can actually load a proper value into OCR0 register. Okay, so let's solve two examples related to what we have talked so far. In the first one, it says, assume the crystal frequency is 8 megahertz and calculate the frequency of the wave generated by the following program. So it sets the port B pin 3 as an output. 100 is loaded into OCR0 for the match value, and R22 is going to be hex 11. So this is going to be loaded into TCCR0, which is going to be a toggle mode, normal, no prescaler. Okay, and we have to generate this wave. Now, the timer clock, let's start with that. The timer clock is given as 1 over 8 megahertz, which is going to be 0.125 microsecond. So this is our period actually that we are having. Now, if I want to draw this, this is going to be like TCNT0 is here, where we have got FF. It's too close to the side. Let's put it here. So TCNT0, this is FF, the highest value that we have in TCNT, and let's set down the bits. So this is 0, and OCR is going to be 100. So that's where we have got the 100, and let's have another dotted line for that, and this is going to be the time. Now, how is that going to count? Starting from 0, okay, it will go up to there, okay, and from there to FF, because this is in normal mode, it's going to change in FF and then down, and then another match, OCR0, and then FF, and then down. Okay, and maybe we can extend this a little bit more. So if we do it this way, and then it will go down, up, and then down. So these are the points that we are going to investigate. Now, how are we going to do that? I want to assign those, but at the same time, I want to draw the OC0 pin, where this is going to be extended as well. So we have got logic 1 and logic 0. Now, what we are looking at is, so OCR 100 is over here, okay? These are the points where OCR is set to 100. Now, if we put those down, because there's the place that's going to be match occurs, and it's going to toggle at that point. Okay, now that means when we start with 0, when it comes over there, the first one, it will be toggling. Then we carry on counting up and overflow, and then down and count up again up to the OCR matches, toggle again, and then stay 0 until it's counting, another match, and toggle again. So 0, 1, 0, 1 is generated. Now, how do we do the calculation? So what we are having here is actually 256 times 1 over 8 megahertz, and 256 times 1 over 8 megahertz here as well, because in total we are counting from 0 to 256. So this wave frequency here, it is going to be 2 times 256 times 1 over 8. So this is what we are going to get as the period of that wave. So if we calculate it, if you calculate that, that's going to be 2 times 256 times 0.125 microsecond as a period. It's going to be 64 microsecond for that wave. And the frequency of that wave, it's going to be 1 over 64 microseconds, which is going to be 15.625 kilohertz, let's say. Okay, so it's going to be 15.625 kilohertz. So this is the wave that we are generating according to this code. So we can see that in normal mode, when match occurs, the OC0 pin toggles and the timer continues to count up until it reaches to the top value. So 100 up to 255, and then down overflow to 56, and then you can see how these waveform is generated accordingly. Okay, so this was the first example. So we already mentioned the CTC mode, which is better than the normal mode for generating the square waves because we can easily adjust the OCR0 register, and we can have adjust the duty cycle of that wave. So let's see an example related to that as well. So that's going to be our example 3. Now you can see that at this point, the frequency of the clock is 1 megahertz, and we need to draw the wave generated by the following program. It looks like a quite long one, and there's an interrupt used. So let's analyze the code first. I'll start with the main. So in the main, the stack is initialized, as you can see, as we are using interrupts. So then pin 3 is set as an output for OC0. And we load this first OCR value as 69. Okay, so the first value is set as 69. And the timer 0 is configured so that CTC mode, no prescaler, toggle on match. And output compare interrupt is enabled from the TIMSK. And the global interrupt is also enabled. So whenever TCNT matches to OCR value, then it will generate and interrupt. So this is the main program starting OCR from 69. Then in the interrupt, whenever the interrupt comes with the match, what will happen? Compare match interrupt occurs, and we decrement R29. So R29 is initialized somewhere. Then it's going to be 0 minus 1, it's going to be minus 1. So if R29 is greater than or equal to 0, we have to go to L1, where we are getting the Z register value from the table, which is going to be 24. Okay, so we have to set the value from the table, and we have to set it to 24. And we have to then, as we are jumping over here, we exit from the interrupt, and then we decrement, we carry on like that until we reach to 24. Whenever we reach to 24, we jump into an interrupt again. Now we have to decrement R29 because R29 is set to 3. Okay, so 3 minus 1 is going to be 2. So moving to the next value, it's going to be 49. Then we count to 49, and then we generate another interrupt. And then it's going to be 1, and then we count to 39, and so on and so forth. Okay, so this is what the code is given to us. And how are we going to implement that or draw the wave for it? So once again, we have got TCNT 0. And we have got a couple of OCR values. So FF is here. I'll just put that over here. That's the highest point. Now we have got a couple of values, 69, 24, 49, 39, and 34. So we have to set those accordingly. So maybe I should erase that until I set those values. So the highest is, let's put that down first, is 69. So let's put 69 somewhere here. I'm just trying to be more colorful so that we can distinguish the signals going on, or the values. Then we have got 49 as the second highest. So 49 is the second highest. And then we have got 39. And we have got 34. Maybe closer than that. And we have got 24. So these are all the values that we have got in the table in total. So that will be the values that the OCR is going to look at in the lookup table. Okay, on the other side, we have got OC. OC 0 pin. And that's going to be 1 and 0. Right, so let's start. It will start with 69. So the first value has to reach to 69. So this is 0 point. That means we have to reach to 69 first. And then we have to roll down because it's in CCC mode. When it reaches to 69, it will go down. And then the first value in the table is 24. So we have to jump to 24. And then 49. And then 39. And then 34. So you can see how our wave is different as a duty cycle by changing the OCR values. So we have to look at each of those points now that we have got compare match. So we drop down those points, each of those points. Okay, and then all we need to do is we have to toggle it because it's a toggle on match, and we can generate the waveform. So again, starting with 0, then we toggle it. Another match, we toggle down, and then stay 0, then toggle again, and then high, and toggle again down, low, and high again. Okay, so you can see how the frequency is different. So you can see here that this part is 70 clocks. This is 25 clocks. This part is 0 to 4950 clocks, 50 clock, and then we have got 0 to 3940 clock, and we have got 35 clock, and this actually going to repeat. So it will repeat from here. I'll also mention that. So going back to the beginning of the table, it will go to 24 and down. Okay, so this is how we are generating a wave according to this code given. Okay, so timer 1, timer 2, timer 3 can also be configured in a similar manner in order to generate a waveform. And you only need to configure the control registers and find the appropriate value for the OCRNs and watch out the interrupt service routines.